the remainder theorem. And this is actually really, really cool in my opinion. If f of x is divided by x minus c, the remainder is f of c. This is actually really incredible that this works out. If a polynomial f of x is divided by x minus c, the remainder is f of c. How could we use this? Well, let's say we have f of x equals x to the fourth plus 6x cubed minus 12x squared minus 30x plus 35. Let me actually write that a little bit smaller. Minus 12x squared minus 30x plus 35. There, I got it all on the screen. I want to find f of 2. Up until now, the only way we know how to find f of 2 is to plug 2 in everywhere. 2 to the fourth plus 6 times 2 cubed minus 12 times 2 squared minus 30 times 2 plus 35. And if I'm plugging 2 in, 2 to the fourth would be 2 times 2 times 2 times 2, that's 16. Plus 6 times 2 cubed is 8, minus 12 times 2 squared is 4, minus 30 times 2 is minus 60, plus 35. And that's 16 plus 48, minus 48, minus 60 plus 35, plus 48 minus 48, bye-bye. 16 minus 60 plus 35. 16 minus 60 would be negative 44 plus 35. Negative 44 plus 35 would be negative 9. So f of 2 is negative 9 for plugging that stuff in. If I wanted to find f of negative 7, well, then this becomes bad, because then we're doing negative 7 to the fourth. That's a really big number. We're doing negative 7 cubed. That's a really big / small number. So on and so forth. The bigger the number, the harder it is. I want you to remember, I'll put it up here. I want you to remember that f of 2 was negative 9. Watch this. This is what the remainder theorem says. If I want to find f of 2, that's going to be the remainder for when I put 2 in the box and I do synthetic division. So 1x to the fourth plus 6x cubed minus 12x squared minus 30x plus 35. Multiply and add. Bring down the first number. 2 times 1 is 2. Add. Multiply. Add. Multiply. Add. Multiply. 2 times negative 22 is negative 44. 35 minus 44. What's that? Negative 9. That was a lot easier than plugging the 2 in. Now imagine the bigger the number, the easier this becomes for finding it. So I mentioned f of negative 7. If I plug negative 7 in for x and actually look for it long ways, like I said, it's difficult, but we would end up, believe it or not, getting 0 once all was said and done. How could we find that using this remainder theorem? Well, I can put negative 7 in the box and I can set up 1, 6, negative 12, negative 30, positive 35. Bring down the first number, multiply, and add. Multiply, careful with the signs, and add. Multiply, and add. Multiply, and add. What's the remainder? 0. So what's f of negative 7? 0. It's incredible, right? Let's do a couple more. Let's change f of x up. F of x equals x to the 4th plus x cubed minus 6x squared minus 5x minus 15. Let's use the remainder theorem to find f of 5. Well, we want to use the remainder theorem. We don't want to plug 5 in everywhere. 5 to the 4th, 5 cubed. These are big numbers we're dealing with. It's a lot easier. Just put 5 in the box. Set up synthetic division. 1, 1, negative 6, negative 5, negative 15. Bring down the first number. Multiply and add. Multiply and add. Multiply and add. Multiply and add. The remainder is 560. So f of 5 is 560. Yep. Same answer as if you plugged in 5 for x everywhere and figured it out long way. A lot faster. What an amazing, amazing outcome. Finally, f of negative 3. To find f of negative 3, I put negative 3 in the box. Same setup. Coefficients. 1x to the 4th, 1x cubed, negative 6x squared, negative 5x, negative 15. Bring down the first number, multiply and add. Multiply and add. Multiply and add. Multiply and add. Remainder is 0, so f of negative 3 is 0. let's use the remainder theorem to determine if the given number C is a zero of the polynomial. Now, what does this statement mean for us? What does it mean? Well, if we had the polynomial say f of x equals x squared plus 6x plus 8, we can factor and set equal to 0. This is x plus 4 times x plus 2. The zeros here would be x equals -4 and x equals -2. The zeros are things that we get when we set the function equal to 0 and solved for x. So -4 and -2 would be zeros of the polynomial x squared plus 6x plus 8. And if we did -4 in the synthetic division, bring down the first number, multiply and add, we see we get no remainder. No remainder because it divides evenly. This is a 0. It comes from an even factor of the polynomial. -2 being a 0 would also give us a remainder of 0 when we divide. Bring down the first number, multiply and add, remainder of 0. So we're going to look at some polynomials. We're going to check and see if we get a remainder of 0. And if so, that number will be a 0. So that's going to be our new usage of the remainder theorem. If we have f of x equals 2x cubed minus 4x squared minus 13x minus 9, and we were looking to see if c equals 4 would be a 0. That means we're doing synthetic division by 4 on 2x cubed minus 4x squared minus 13x minus 9. Bring down the first number, multiply and add. Multiply and add. Multiply and add. 3 is a remainder here. The remainder is not 0. Therefore, 4 is not a 0 of this function. Okay, we're going to make this a little less fun. I know you've been waiting for it. You've been saying, you know what? This synthetic division stuff is pretty easy. Just multiplying and adding. How hard can you make multiplying and adding? We have f of x equals x cubed plus x squared minus 3x minus 3. We're going to check to see if c equals radical 3 is a 0. Yeah, I did that. We're putting radical 3 in the box. What's in the box? Radical 3. We are synthetically dividing by radical 3 the polynomial 1x cubed plus 1x squared minus 3x minus 3. Bring down the first number. These ones feel excessive. Bring down the first number. Multiply. Radical 3 times 1 is radical 3. Add. I'm sorry. 1 plus radical 3. Don't pull out a calculator. That's going to defeat the purpose of this entirely. 1 plus radical 3 is just 1 plus radical 3. Multiply. Radical 3 times 1 plus radical 3. Distribute. It would be radical 3. Let's actually write this out. So pretend we're in another space here. Radical 3 times 1 plus radical 3 would be radical 3 plus 3. Or written with the radical second, 3 plus radical 3. We're back. 3 plus radical 3. Add. Negative 3 plus 3 is 0. 0 plus radical 3 is just radical 3. Oh, wow. Is this really going to work out so nice? This is fantastic. Radical 3 times itself leaves us with underneath. Leaves us with what's underneath. Radical 3 times radical 3 is just 3. Negative 3 plus 3 is 0. There's no remainder, which means radical 3 is a 0 of this polynomial. Isn't that exciting? Wow. Our next function is f of x equals x cubed plus x plus 10. And we're going to check c equals 1 plus 2i. It's a complex number. Now, if you need review with complex numbers, that's from the previous course. That review video is available where I have made previous course videos available to you. This isn't going to change what we do. We are doing synthetic division on 1 plus 2i. Remember, i's work just like x's, but because I equals the square root of negative 1, that means whenever we get an I squared, that becomes a negative 1. So times I squared is times negative 1. We have to make that change and work further. Otherwise, i's work just like x's. It means we're not dealing with real numbers here. We're dealing with one step beyond real numbers, the complex numbers. All of our real numbers plus imaginary numbers, because the people who named it were real creative, just like me. X cubed, we have 1x cubed, 0x squared. Make sure you leave the placeholder. 1x plus 10. Bring down the first number. Multiply 1 times this thing. 1 times 1 plus 2i is 1 plus 2i. Multiply and add. 0 plus 1 plus 2i is 1 plus 2i. Okay, that's not so bad so far. I'm sorry. 1 plus 2i times 1 plus 2i. Now we're going to go back to the land of, imagine a different area on your page. I just want to keep working here. This is down across somewhere. 1 plus 2i times 1 plus 2i. We would FOIL these. First, 1 times 1 is 1. Outer, 1 times 2i's plus 2i. Inner, positive 2i times positive 1 again, positive 2i. Last, 2i times 2i is positive 4i squared. So this is 1 plus 4i, 2i plus 2i is 4i. But plus 4i squared is plus 4 times negative 1. And positive 4 times negative 1 is negative 4. And 1 minus 4 is negative 3. Negative 3 plus 4i. Negative 3 plus 4i is what we get when we multiply 1 plus 2i times 1 plus 2i. Now we add 1 plus negative 3, 1 minus 3, that's negative 2 plus 4i. And now again, 1 plus 2i times negative 2 plus 4i. I'm going to go to the imaginary area that's off somewhere again. 1 plus 2i times negative 2 plus 4i. One times negative 2 is negative 2. 1 times 4i is plus 4i. Inner 2i times negative 2, that's negative 4i. Last 2i times 4i plus 8i squared. That was negative 2 plus 4i minus 4i plus 8i squared. Plus 4i minus 4i cancel each other out. So we have negative 2 plus 8i squared. That's negative 2 plus 8 times negative 1. That's negative 2. Positive 8 times negative 1, that's negative 8. Negative 2 minus 8 is negative 10. So negative 10 is what we get when we multiply this times this. 10 plus negative 10 is 0. So all of that very careful work, we get a remainder of 0, which means yes, 1 plus 2i is a 0 of this function. Now, for the case of 1 plus 2i being a 0, what exactly does that mean? That means that x equals 1 plus 2i is an answer for x when the function equals 0. So this function, the x cubed plus x plus 10, when it equals 0, one of the factors must be x minus 1 plus 2i. X minus the entire 1 plus 2i. Why? Because x minus the entire 1 plus 2i set equal to 0, adding it to both sides would give us the answer of x equals the 1 plus 2i. So what does this factor look like even further? And then there'd be other factors as well. We don't care about those right now. We're just looking at this one. X minus 1 minus 2i might be another way of looking at that. But x minus the complex number 1 plus 2i, that would be one of the factors. X minus a 0 is always a factor because that is what a 0 is. It comes from the factors. So let's take a look at f of x equals x to the 4th minus x cubed minus 11x squared plus 11x plus 12. Let's take what we learned from the remainder theorem and really nail down what we're going to call the factor theorem. So what we were just talking about with the zeros. If there's a remainder of 0 for a 0, that meant that f of that 0 was 0. And we just defined that there we go. So x minus that number c is going to be a 0 when we get 0 when we plug it in. In other words, if we do the synthetic division, we would get a remainder of 0. Let's use this to answer basically the same question we've been doing a different way. Is x minus 3 a factor of f of x? That's an arrow, not a J. Well, to answer the question, is x minus 3 a factor of f of x? What we're going to be doing is checking to see if 3 is a 0. X minus 3, x minus c, c is 3. The thing we're subtracting goes in the box. So is x minus 3 a factor of f of x? We need to recognize that that means the same thing as asking, is positive 3 a 0? In other words, if we do synthetic division by positive 3, 1, negative 1, negative 11, positive 11, 12, Do we get a remainder of 0 or not? If we do, then it's a factor. If not, then it's not. Bring down the first number. Multiply and add. Multiply and add. Multiply and add. Multiply and add. We get a remainder of 0. That means 3 is a 0, which means x minus 3, yes, is a factor of f of x. Let's use the same function. Again, that was f of x equals x to the 4th minus x cubed minus 11x squared plus 11x plus 12. And this time is x plus 2 a factor? There, an actual question. Is x plus 2 a factor? Well, what are we checking to see if it's a 0? If x plus 2 is the factor, x minus negative 2 is x minus c. So we're putting negative 2 in the box for 1, negative 1, negative 11, positive 11, and 12. Bring down the first number. Multiply, add, multiply, add, multiply, add, multiply, add. Negative 30 is the remainder, not 0. So no, it is not a factor. Okay, we're building our skills up. The questions are going to ask us to do more and more complicated things, but we have to understand what we're doing, and these questions are going to make sense. Next, we're going to be told to factor. Not is something a factor, is something a 0. This time we're specifically going to be told to factor f of x equals 3x cubed plus 25x squared plus 42x minus 40, given that negative 5 is a 0. Of f of x. So given that negative 5 is a 0, that means that f of x in factored form has an x plus 5 as a factor, because a factor of x plus 5, when we set it equal to 0, gives us negative 5. That piece of information, that negative 5 is in fact a 0, means we have one of the factors. How can we get this leftover piece? Well, we can synthetically divide. We already know the remainder is going to be 0. It's a factor. Remainders are 0 in that case. But we're interested in the rest of it this time. So -5 in the box, 3, 25, 42, and -40 on the outside. 3x cubed plus 25x squared plus 42x minus 40. Bring down the first number, multiply and add. Multiply and add. Multiply and add. So like I said, we're going to get 0 as the remainder. We know that because -5 is a 0. But what we also got was this 3, 10, -8. It started as a 3x cubed. So this 3 in our answer, we lower the x cubed by 1, remember? And it represents a 3x squared plus 10x minus 8. So our next step is going to be to continue to factor. We have now that f of x is x plus 5, the factor that gives us our 0 of -5. And then from doing the synthetic division, the rest of this is 3x squared plus 10x minus 8. A 3x squared is a 3x times a 3x using the airplane method. Numbers that multiply to -24 and add to +10. That is +12 and -2. Plus 12 minus 2. Nothing can be divided by the 3x and the 2, but here 3x and 12 can both be divided by 3. That's the rest of the airplane method. X plus 5 times x plus 4 times 3x minus 2. And that is a completely factored form. You could have also split 10x into plus 12x minus 2x and did factoring by grouping to get these. But remember, I always use this airplane method. You can find that in my factoring videos, also available where the review videos are from the previous course. Okay. So what use is there in finding what we just did? We found that the factored form was f of x equals x plus 5 times x plus 4 times 3x minus 2. Well, for one thing, if we set it equal to 0, we could continue to solve. We found the other factors. We can find the rest of the zeros. X plus 5 equals 0. X plus 4 equals 0. 3x minus 2 equals 0. X equals -5. We knew that was a 0. We were told that. but x equals -4. 3x equals 2, so x equals +2/3. We can find the zeros. What are zeros when we're graphing? X-intercepts. So if our problem was graph f of x equals 3x squared plus 25, or sorry, 3x cubed plus 25x squared plus 42x minus 40. If it said graph, well, putting it in factored form is going to give us our zeros, our x-intercepts. They all have multiplicity 1, so they're all crossing points. This is a positive 3x cubed, which means that it falls to the left and rises to the right. With the end behavior in the x-intercepts, a y-intercept of -40 by plugging 0 in for x. These are points that we can have to start our graphing journey. So this is all just about getting more tools to help us graph. One thing that I didn't mention before, but I wanted to, I really did, was this idea of number of turning points of a graph. This would be very useful. When I'm talking about turning points, something like this would have 1, 2 turning points. Turns here from increasing to decreasing, turns here from decreasing to increasing. The number of turning points is something we can begin to figure out by, like a lot of things, looking at the degree. If f is a function with degree n, and then the graph of f has at most n minus 1 turning points. So that last f we looked at, it started with like an x cubed, remember? So it has at most 3 minus 1, 3 minus 1, or 2 turning points. Maybe it has 1 turning point, maybe it has no turning points. But at most, it has 2. We have a similar thing that we can tell from the degree about the number of rational zeros. Not just rational zeros. Sorry about that. Number of total complex zeros. And when I say complex zeros, I mean zeros that are both rational slash irrational. And if something is rational or irrational, what do we call it? We call it real. But also the imaginary zeros. The zeros that involve I, like we saw earlier. And the number of real plus imaginary is the number of total complex zeros. That is exactly equal to the degree. So something that's an x cubed, because it's an x cubed, it has 3 complex zeros. Some of them real, some of them imaginary. The imaginary zeros are special because the imaginary zeros come in pairs. Conjugates. In other words, if we had a 3 plus 2i as a 0, that also guarantees a 3 minus 2i. So we're going to use this idea of the number of complex zeros later on as well. Okay, we want to write a polynomial of degree 3 that has zeros of 1/2, radical 6, and negative radical 6. So here's what we do. We build this backwards. If these are the zeros, then we have x equals 1/2, x equals radical 6, and x equals negative radical 6 as the answers to 0 equals x minus 1/2, x minus radical 6, and x plus radical 6. This we know how to multiply quickly using the special formula. Positive, or a plus and a minus, everything else the same. These are conjugates. And when we multiply them together, we get a difference of squares. X squared minus radical 6 squared x squared minus 6. So it's like we're doing the problem backwards. How would we solve this? Well, we'd factor, and it factors as this, but we would never think to factor it like that because that's not one of our special things, but we could think if it was x squared minus 9, that would be x squared minus 3 squared, x minus 3x plus 3. Just instead of 3's, we have radical 6's as the square root of 6. Let's keep going here. Multiply these together. So the next line underneath x minus 1/2 x squared minus 6 would be to FOIL these. X times x squared is x cubed. Outer, x times negative 6, negative 6x. Inner, negative 1/2 x squared. Last, negative times negative is positive. 1/2 times 6 is 3. And then I'm going to go ahead and put it in decreasing power of x. And what would we have set equal to 0 here? We would have set f of x equal to 0. And there we go. We just created a polynomial f of x of degree 3 that has the zeros. 1/2 radical 6 and negative radical 6. Now, this is not unique. In front of that factored form, what if we put a 2? Doesn't change that we got the 3 zeros we needed, and it wouldn't give us an additional 0 because 2 equals 0. That's no solution. We throw that out. What if there was a negative 4 in front? They might flip the thing upside down, but it's not going to change the 3 zeros. So keep that in mind. It's not the only answer. It's just one of the possible answers. We can multiply the whole thing by 2. We can multiply the whole thing by negative 3. It won't change the zeros we have. It would just be a form of a vertical stretch.